All right, good morning. As others of us filter in, I'd like to say, ladies and gentlemen, good morning. A year ago, Mauricio Castillo thought to discuss how does the brain think. We are very fortunate indeed to have with us world-renowned neuroscientists who have accepted our society's invitation to discuss this topic with us. Following a short wake-up call on the ascending arousal system by myself and Dr. Zhang-Hee Cho of Korea, Dr. Karl Zillis, professor of brain research at the University of Aachen and research center at UIT, Germany, will discuss the anatomic substrate of thought, the cytoarchitecture, the myeloarchitecture, the chemoarchitecture of the brain. After that, Dr. Jeremy Schmamann, professor of neurology at Harvard and at Massachusetts General Hospital, will address the circuitry that enables thinking. Together, we hope that our talks will enable you to enter the burgeoning world of neuroscience and perhaps enhance your own thinking. The ascending arousal system is necessary. Purposeful thought requires wakefulness. The centers involved are the tegmental centers in the mesopons relating to the thalamus, nuclei in relation to the mammillary body, tubercinarium and fornix, ventrolateral preoptic areas, and the basal forebrain. The mesopontine centers include the pedunculopontine and lateral dorsal tegmental nuclei, which are acetylcholinergic, the locus ceruleus, which is noradrenergic, and raphe nuclei that are serotoninergic. There are thalamic centers, the reticular nuclei, and the interposed interlaminar nuclei that have mixed transmitters, and hypothalamic nuclei, the tuberomammillary nucleus, which is histaminergic, the perifornicile nucleus, which is orexinergic, and the ventrolateral preoptic nucleus, which is GABA and GABAergic. Then the basal forebrain, again cholinergic. If we look at the group of the tegmental mesopontine nuclei, the pedunculopontine and lateral dorsal tegmental nuclei form a dorsal tier in relation to the inferior colliculus and just below. The noradrenergic locus ceruleus forms a column at the upper pons and midbrain, and the raphe nucleus, serotonergic, are in this ventral tier as well. The pedunculopontine nucleus, CH5, lies in relation to the inferior colliculus and the tegmentum extending down to join the group of CH6, which is the lateral dorsal tegmental nucleus. The locus ceruleus forms two columns containing melanin and appearing bluish in the upper pons and midbrain, and the raphe nucleus lie in the midline, particularly here, the median raphe nuclei of the nucleus centralis superior and the dorsal raphe nucleus. If we look with imaging, we can begin to see the area of the raphe nuclei, of the pedunculopontine nucleus, but not resolve it individually. The pedunculopontine and lateral dorsal tegmental cholinergic nuclei pass by the medial forebrain bundle to the thalamus to modulate thalamocortical and cortical-thalamic connections. We see grossly that the thalamus has an external medullary lamina and an internal medullary lamina, dividing it into mediodorsal and ventrolateral groups. External to the external medullary lamina, there is a hemisphere of the reticular nuclei encompassing the thalamus. While we don't see them well with 3 Tesla, at 9.4 Tesla, you see a robust globe or hemisphere of the reticular nuclei of thalamus interposed between the cortex and the thalamus, with the thalamocortical and corticothalamic radiations passing through, modulated by and gated by the reticular nuclei. Diagrammatically, the reticular nuclei are interposed between the cortex and the thalamus and are arranged somewhat topically in different areas for sight, for touch, for hearing and motor and limbic systems, gating the input and output to the cortex. In addition, between the medial and the ventrolateral group, within the internal medullary lamina of the thalamus, we see central median and parafascicular nuclei, which are involved with the ascending arousal system. With 7 Tesla susceptibility-weighted imaging and 2-deoxyfluoroglucose imaging and superimposition of the two, we're beginning to resolve well the individual nuclear groups of the thalamus, including the central median group of the interlaminar nuclei. The locus ceruleus is the noradrenergic nucleus in the ventral tier of these sleep-wake centers. You can see it as a cross-section of a column in the high pons and midbrain, and because of the neuromelanin, it shows up well on 3 Tesla T1-weighted imaging. If you look with 9.4 Tesla, you find the locus ceruleus deep to superior cerebellar peduncle and mesencephalic tract of 5, just at the lateral edge of the high 4th ventricle and aqueduct. The serotonergic dorsal raphe nuclei, centralis superior and dorsal raphe nucleus, form part of the ventral tier of the mesopontine group. These are arranged, as you see here, in groups B1 to B9 in the tegmentum of the stem, and again, with 2-deoxyfluoroglucose, you can begin to resolve them, and with a new unpronounceable ligand, abbreviated carbon-11 DASB, you can actually resolve the individual raphe nucleus and project them onto the 7 Tesla imaging to see them well. In the region of the hypothalamus, we have excitatory histaminergic tuberomammillary nucleus in relation to the mammillary body and tuber cinereum, the excitatory orexinergic perifornicele nucleus in the lateral hypothalamus, and the inhibitory GABAergic and galinergic ventrolateral preoptic area right here in the lateral hypothalamic region. Comparing the Klinger technique with 3 Tesla ex vivo MR, we can see the fornix pass down to the mammillary body, the principal mammillary fasciculus arise, the mammato-tegmental tract coming back to the mesopontine centers, and the mammallothalamic tract passing to the anterior nucleus of thalamus, whence fibers go throughout the brain from the anterior thalamic nucleus. Looking at the region of the mammillary body, the perifornicele region, and the ventrolateral area, you can see that the tuberomammillary nucleus diagrammatically lies here, and this is the histaminergic wake center. This parafornicele area is the orexinergic waking center as well, which works with the tuberomammillary nucleus, and then a sleep center, the ventrolateral preoptic area, which is GABA and galinergic. Human sleep includes wakefulness, several stages of non-REM sleep culminating in slow-wave sleep, and then interrupted by periods of REM sleep, which are like unto wakefulness, but with inhibition of all muscle activity except for the eyes and the diaphragm. If we look, the tuberomammillary nucleus is our wake center. It's a histaminergic nucleus that works with the ventral tier of the ascending arousal system. That works then with the noradrenergic locus ceruleus and the raphe nucleus, which are serotonergic, to promote wakefulness. The ventrolateral preoptic area in this region is our sleep center. It initiates and maintains non-REM sleep. Subgroups of the nucleus innervate and inhibit the tuberomammillary nucleus and the ventral tier of locus ceruleus and dorsal raphe nucleus to help govern sleep-wake cycles. The cholinergic pedunculopontine and lateral dorsal tegmental nucleus are the REM sleep center. Alone, they act to induce REM sleep. The locus ceruleus, nucleus centralis superior, and dorsal raphe nucleus of the ventral tier tonically inhibit the pedunculopontine and lateral dorsal tegmental nucleus until local GABA interneurons inhibit these, thereby disinhibiting the cholinergic nuclei, allowing them to initiate REM sleep. All of these are interconnected by fiber tracts passing from the basal forebrain and the hypothalamus down the tegmentum, which goes in part by the name of the median forebrain bundle. This is an early attempt to display it. Dr. Cho of Korea has resolved these better, looking at the corpus callosum, anterior commissure, the fornix coming down to the mammillary body, and the optic chiasm here. You can see that you have separate bands of fibers passing up from the mesopontine tegmental centers to the tuberomammillary and perifornicele areas, and from these up to the thalamus and throughout the basal forebrain. These enable the transmission of these multiple retrograde and anterograde impulses between the areas. In summary, in diagram, we have the mesopontine brainstem centers, the dorsal tier of pedunculopontine and lateral dorsal tegmental nucleus, which are excitatory, the locus ceruleus, noradrenergic, and the serotonergic centers. These influence the thalamus and the basal forebrain to promote sleep, to promote wakefulness. Tuberomammillary wake center stimulates thalamus for wakefulness, and the ventrolateral preoptic area initiates sleep. Together, they work in a circuit to promote cycles of sleep and wake. While many of these names are new to you, perhaps, even some of the neurotransmitters may be new, this is simply the beginning of what will be a wave of neurocognition and a wake-up call for us to all learn the deep brain and the basal ganglia, the hypothalamus, and the basal forebrain. Thank you very much.